Okay, so welcome to the afternoon session. Our first speaker is Dimitri Gangardt from University of Birmingham, and he will tell us about limit shapes and their phase transitions, classical and quantum. So.
Okay, thank you. Thank you for inviting me here. It's such a wonderful place and such a nice conference. And in this talk, I'm going to talk about some recent, not so recent developments which appeared in our collaboration with my former and present PhD students, diploma students, yes sir, Dylan, Sen, and James, as well as my collaborator Alex Abanov, whom you all know, I presume, and Alex Kamenev. So, limit shapes. Yes, I give a very informal definition. It's a formation of a non-random shape in a thermodynamic limit of a random statistical system, and characterized by sharp boundaries. And there are plenty of examples of such systems in statistical physics, like equilibrium shapes of crystals, random tiling, directed polymers, on more mathematical side, and random Young tableau, which appear in the presentation of large groups. And there was a lot of very vast literature, which I will not be able to overview, starting with some mathematical developments by Versh and Kerov, so physicists like Macroscopic for the crystals, and so on and so on and so forth. Some people are in this audience. And okay, so let me give, probably I just will come to maybe the first example of a limit shape which appeared more than 100 years ago. And it's a beautiful, beautiful solution of a problem of an equilibrium shape of a crystal if what is given is the surface tension as a function of the direction here, like gamma. And it's known as, under the name of Wolf construction, under the name, after the name of chemist Georg Wolf, who solved this problem by essentially proposed a method to draw this equilibrium shape here in 2 dimensions. It essentially goes like drawing a perpendicular line to the direction, each direction at the distance proportional to the surface tension, and consider the envelope of all such lines as one changes the direction. And this construction is some variant of a Legendre transform, and is well known in Legendre transform. The smooth curve of gamma theta translates into the curve which might have singularities like cusps here. And in 3 dimensions, that leads to formation of a flat frozen facets, and there are some non-flat and fluctuating regions. These fluctuations are interesting, studied quite extensively. And this is probably the first example of limit shape. I'm not going to spend much time on this. I will give you another example, which can be very easily visualized and actually simulated. Namely, let's start with the following problem. Let's take a checkerboard and try to cover it with 2x1 rectangles in a closed packed way. Of course, there will be a lot of configurations. Let's draw a typical configuration for the beauty of the picture. I will, in fact, consider that there will be 4 different types of the tiles, 2 vertical with like black square on top, on the bottom, and 2 horizontal with black square on the left, on the right and on the left. So by using these color dominoes, I can produce a random typical configurations of such a tiling. And in the case of a square, there is nothing really interesting about it. Namely, as one increases the size of the board, one goes to some sort of noisy picture, which some remember when the television were analog and late at night or just not working. That's what one was able to see. However, let us now change the shape of the board we want to cover and take it in the form of some well-known so-called Aztec diamond. You see, pretty much obvious what I've done. I just removed the corners. And in this case, by producing take another typical configuration, I start to see something very, very interesting, namely the limit shape. Here, it's not very clear, but already one can see that the red dominoes goes mostly to the top, blue to the bottom, yellow to the left, green to the right. If I increase the size, the structure is preserved, and there is a interesting some randomness in the middle. And if the size of the board is sufficiently large, one can see the emergence of a circle. One can show that it's a circle. Actually, it's a subject of the theorem by these people and known as the Arctic Circle theorem. All this new beautiful picture, including the rectangular one, can be simulated very easily by going to the website and running different parameters. It will produce plenty of them and even more exotic ones. All right. So I want to study these configurations, and I want to look at their properties. I also would like to see what happens when some parameters change in this picture. For this, as someone from the quantum background person or dynamical system background, I would like to map this problem onto something which is familiar to me. Namely, I will start mapping these tiling configurations to configurations of moving particles. And again, I will just use the picture of how to do that. Let's take this example of a tiling of a Aztec diamond. Let us complement the left-hand side by the kind of wall of red bricks, the right-hand side by the wall of green bricks, such that these corners are just match these walls. Now let us make these bricks thinner. So I have this kind of picture now fully equivalent to this one. And now I will finally superimpose my configuration with a configuration made of only red bricks. So just a total wall of all red bricks everywhere. And in this construction, the structure of some lines which are wiggly and moving from, say, bottom to the upwards is emerging. Here, the lines are completely straight because here I have only a regular pattern of green bricks. Here they are broken, means that nothing goes there. So looking at this, and just another way of representing this, I understand it will be by using some sort of polymers, lines, or trajectories of particles, starting from the right-hand side of my space, ending also on the same positions. It can be actually rigorously proven that the configurations and these lines can be described by a certain dynamics of free fermions, namely their evolution in imaginary time, precisely like in the talk of Jerome. Here, just a more beautiful example, which Sasha produced using ChatGPT. He taught him how to produce these things. And it's really nice. So this is, again, a configuration of Aztec diamond. Just 32 by 32 is better than my primitive picture. All right, so this is as you can see, what happens here, there's a right-hand side, which is completely motionless. Particles just don't move, they're frozen. And some trajectories fluctuate away. So it can also be some configuration which makes you think about a SEP kind of problems. And this region is completely empty. This is where the holes live, and I don't draw them. Right. A similar problem now in quantum setup was proposed and solved by Abanov, but following attempts of integrable community to calculate so-called emptiness formation probability in the case of spin chains. Typically, this corresponds to having a ferromagnetic string in an antiferromagnetic ground state. In the language of fermions, I will consider the ground state of fermions on the line and ask a simple quantum mechanical question: what is the probability to have an empty region appearing spontaneously in such a state? And there is a nice mathematical way I can map this problem onto the problem of calculating such an expectation value, namely the probability of having this region is called emptiness probability, can be obtained by taking the operator e to the minus s, here the operator which counts all the particles on this interval, and taking parameter s to infinity. Again, by thinking about this problem and representing the ground state as sort of path integral in the imaginary time of my fermions, I will arrive to quite a similar picture to that one I obtained for the Arctic Circle. Namely, I will ask the particles starting from the bottom, going up in imaginary time. Here, their position are actually random because they have some sort of mean density fixed. Their position are not fixed, unlike here. And this particle have to avoid the interval, which for convenience is placed at imaginary time tau equals to 0. Both these problems can be mapped on quite a similar way onto imaginary time evolution of free fermions. And therefore, we have the apparatus of quantum mechanics at our disposal to calculate these things. And I will do that at some point. But before I'm doing this, I will ask myself whether these results can be obtained since my fluctuations here are very, very large. My limit shapes are very macroscopic. It would be better to use some effective description. And of course, hydrodynamics comes to mind. And I will use it. Okay, I forgot one slide, sorry. So this is, before I go to the hydrodynamics, I just wanted to say that in this type of path integral, I, of course, have a large parameter, namely, for example, size of my radius of my Arctic Circle, or the size of the interval, which I can use to my advantage. And in this case, the calculations will become semi-classical, and all these random configurations will be dominated by only one, which is nothing but an instanton. And here is an example of such instanton configuration for the Arctic Circle. So particles will go, this is the instanton configuration for Arctic Circle, and this is the beautiful picture of configurations of lines going around the interval at tau equals 0, producing the emptiness. So as you can see in both these figures, the shapes I obtain are two-dimensional, and in particular here, even though I'm talking about one-dimensional fermions, because I have an extra dimensions of imaginary time, and my particles sort of have a memory, they cannot go back to their positions immediately and then produce such a limit shape. And that's what makes this problem of emptiness similar to the problem of Aztec diamond covering. And now I'm going to use the machinery of hydrodynamics. For this, I'm not writing the action. Maybe I should have, but I didn't have time. And it doesn't really lead to anything because I'm going to use the classical solutions. And classical solutions are essentially the hydrodynamic equations. And the hydrodynamic equation can be posited this way, quite standard. Namely, I will define Riemann invariants density plus here the imaginary I or imaginary time plus velocity as a function of position and time. And these quantities obey complex Burger's or Hopf equations. This equation and the complex conjugate, if you add them and subtract them, you will obtain the standard continuity equation and Euler equation for free Fernans. And solution can be written straight away. It's solved by characteristics. Namely, one writes this kind of ballistic formula, x plus velocity times I tau equals, and the right-hand side is the most interesting object in my talk, because now this is a problem-specific function of the Riemann invariant K. And for example, and I will find this function, and this is all I need to know to solve my problem. So for example, if I want to reproduce Arctic Circle configuration, I have to take, and there is a nice explanation which I skip, x0 of K, the right-hand side, to take the Hilbert transform of the dispersion, of the derivative of the dispersion relation, namely cos K, and solve for complex number K as a function by fixing x and tau. That's it. It's a very simple construction. Okay, so the boundary condition is that my function, it depends on the problem. So in the case of emptiness, for example, I have actually, I have to fix my density to be 0 on the interval, and also to converge, and so I have also imposed boundary condition and space and time infinity. Good. So what does it give? So I'm continuing with my program. I'm solving this equation. In this simple case, this equation has two roots, which are related by the symmetry plus minus rho. But these two roots can be either, in this case, sort of either purely imaginary or have positive and negative real part. In the frozen region, it will be defined rho as rho equals to 0, or rho is a full occupancy equals to 1. In the fluctuating regions, rho is between 0 and 1. In particular, it's very easy to get this from this equation, the equation for the boundary. Namely, one have to impose the degenerance. I mean, for certain values of x and tau, these two roots coincide, degenerate, and this corresponds precisely to the boundary of fluctuating region. In this way, I can take my k equals to, let's say, 0 plus IV, substitute my equation, it becomes a real equation. That's one equation to fix two variables x as a function of tau, and the second equation is the condition for the degeneracy of the roots. In this way, I can represent my solution as an envelope of straight lines defined by the first equation as I change the parameter b. And this has very similar meaning to and very similar to the Wolf construction as well. And again, it's nothing but Legendre transformation from the function given by the right-hand side of this equation, let's say g of v, the function x of tau. It's a Legendre transform. Okay, similarly, solution for the emptiness can be obtained. And this is the picture which has already appeared here. This is the optimal fluctuation, which was obtained by Abanov as a function of space and time, and has shape of the boundary. If I look from above, which has a nice mathematical property, it is an asteroid. And asteroid, for those who don't know what it is, it's just the figure which is produced by rolling a small circle inside a bigger circle with 1/4 of the radius ratio. And this way one can also calculate not only the shape of the optimal fluctuation, but also evaluate the action, and putting it into the exponent, one obtains the leading asymptotics of the emptiness formation probability. And its interpretation is pretty nice, because this way of this sort of free energy, if you wish, is given by the number of proportion to the number of expelled particles squared, or the area in the space time of the asteroid. Good.
So the since you were thinking of fermionic particles evolving in time, so there is some relation between fermionic trajectories and Young tableau evolutions, and there is some story of melting that one knows, and critical shape from the story of melting of Young tableaus. Is there some relation?
Absolutely.
Okay, I see.
Absolutely, I'm quite sure it is. Even though I'm not aware of this particular problem.
Yeah.
But there is a famous problem, and Kazakov-McDouglas presentation, for example, which deals with Young tableau and their dynamics as well. So I'm going to my second part, which is the phase transitions in these objects. And for this, I just would like to recapitulate. So what we have here, we have a solution of the hydrodynamic equation in this ballistic form. We need to fix the right-hand side. So essentially what it means to some extent is to give particles at tau equals 0 certain momentum and propagate them in imaginary time. The time reversal symmetry present in this problem means that at tau equals 0, the momentum k is real, represents the density. So this function is nothing but the inverse density profile. If I inverse this function, I will get rho as a function of x at tau equals 0. For Arctic circle, as I said, it's given by the cos k. Here I have reintroduced the radius of the circle. In the emptiness problem, it's given by this function, and I will tell you how to obtain it. And this is the beautiful picture of the emptiness instanton for the lattice problem as well. So you can, here, for example, in addition to the empty region, which is blue, you can also have completely full regions on the sides. But these functions were obtained by essentially a guesswork. Is there any sort of industrial way to calculate them? Typically, it's quite a difficult problem, because boundary conditions, again, imposed at, say, at ends of the intervals, and one has to find the optimal configuration at tau equals to 0. Right, so there is a solution to this problem, at least for these two and some others. Let us do exact fermionic calculations. After all, quantum mechanics was in our curriculum, so we can do this. Namely, let's take now again, the state for Arctic Aztec diamond, but now, instead of filling all the right-hand side with the particles, I will take only a finite interval, because I can't do the calculations for infinite number of fermions. Some people can, I don't. And I will take the number to be n, so we'll introduce another parameter in the problem, and represent this quantum mechanical state as just standard way of fermionic operators acting on the vacuum. Calculate this object, and this object actually can be calculated using Wick theorem, and one gets a determinant by counting all the possible convolutions. And it also becomes it's not a simple, it's not just the determinant, it's a Toeplitz determinant. It depends only on the difference of J minus L of row and the column of such an object. Well, Toeplitz determinants are easily calculated, but that's not our goal, and there is, again, huge literature devoted to this. We would like to represent this, the Toeplitz determinant as something which allows a asymptotic expansions. Namely, one represents the determinant, the so-called Andreev Andreev identity by a n-dimensional integral of exponent having this energy in the exponent, and this energy is nothing but the Coulomb gas. So particles on a unit circle interacting via repulsive logarithmic interactions under the action of the external potential. External potential, of course, represents the dispersion of the free fermions, and this structure here comes from the determinantal structure of our object. And if one again searches in the literature and gives ChatGPT to say what is this, one finds that this is nothing but the Gross-Witten-Wadia model, which appeared in a completely different context, lattice QCD, and the results were well known. Now, here, what again? Let's see. We have charges on the unit circle. We have external electric field acting in this direction. So what one expects from the physical grounds? Well, first of all, one can solve this problem and find the optimal distribution of charges in the asymptotic large n limit. Additionally, there is an interesting feature, quite exciting, that as I increase the electric field, more and more particles piles in this size, on this side, and less particles are on the opposite side because they won't go to the minimum of the potential. And at some critical value of the electric field, there is a gap opening in around k equals to pi. And this is famous Gross-Witten-Wadia transition. As you can see, well, here it's just inverted, but anyway, if I define the density of the particles, I have two cases for lambda, and lambda is the parameter which essentially measures the ratio of number of particles to the propagation time, of the vertical size of my circles, so the radius of my circles. And in one case, when lambda is small, one has only a portion of the intervals from minus pi to pi supporting the charges. And the other case is the full intervals, so it's covered by the charges. Good. Now, here comes the crucial, okay, so this is a third order phase transition as was shown by Gross-Witten and Wadia at lambda equals to n equals to r. What is, now the hint, what is this, what does it mean for our Arctic Circle limit shape picture? It's not very difficult to guess. Each side of each kind of domain wall here produces an Arctic Circle, and then they're symmetrically. And if these 2 points are sufficiently far away, these Arctic Circles are living their independent life. And I simply have to take them into account independently. However, when number of particles becomes small or r becomes too large, the circles move closer together, touch, and something else appears. What does appear? Well, the answer is actually contained in the solution of the Coulomb gas problem. The simple argument goes like that. Essentially, maybe I should explain it here. I will probably use the argument that unlike usually what is represented here, this is the momentum from minus pi to pi, and this coordinate is x. So when lambda is very large, that means that my electric field in the Coulomb gas is very small. And in this case, I'm starting from flat distribution of charges. X is in fact, so the spoiler is the X is nothing, the X of K is the density of the charges on the previous on the previous slide here. Then the electric field changes the distribution of charges, and they pile up around k equals to 0. At some critical value of lambda, these two curves meet at plus minus pi, and after that, some sort of gap opens. If I think in terms of what I'm representing here is at the same time is the Wigner function of my fermions, the droplet, which Gautam was talking about. If I sum the function horizontally, I am supposed to get a density of my particles as a function of position x. If I sum them vertically, I get a momentum distribution, but I'm not interested in this one. So the density has two regimes. In this regime, which corresponds to lambda smaller than 2, my density is nice and smooth. It's similar to Wigner semicircle. I have just rotated the picture by 90 degrees. In the case for the lambda greater than 2, actually my density has a flat plateau. As I said, what I'm showing here, I remind you that k is essentially proportional to the density. So what you can see here is the transition between two fluctuating regions. Think about the Arctic Circle and two Arctic circles actually, and cut it at tau equals to 0. So as I go from this side to the other side, first I start with a 0 density, then I go to the fully occupied region and end up with another fluctuating region and 0 again. Essentially, I can just borrow this function from the Coulomb gas problem, substitute to my ballistic solution of the hydrodynamic equation, solve it. Now it's more complicated. I need to use Mathematica for that. This is essentially Wigner function of the fermions, and this is the density if I just integrate it in this direction.
So if you look at it that way, it's a
Yeah.
big function.
So I'm plotting density as a function of x, but in a very kind of unusual way, vertically.
I think
I trust you can mentally rotate this picture. Okay, so this is what happens. Nice pictures. So this is a situation where lambda is greater than 2. Two Arctic circles, their density, and this is our limit shape, just looking from above. This is what happens when lambda is smaller than 2. There's a kind of nice cusp appearing. And it has many other properties which one can talk about, but I don't want to. So one get this. So this is the kind of space-time resolved picture of Gauss-Witten transition. Are there any questions? Right. So the fact that the transition is of third order can be actually inferred simply by simple estimate. Let's concentrate on the central part slightly after the transition happened. So delta represents the distance from the critical value of the parameter lambda. First of all, I can say the following thing. So essentially, I claim that everything, it depends on this small central region. This region is very small. Delta is very, very small. The area in which the density is different from what it was before the transition, namely rho equals to 1, is given horizontally by delta and vertically by square root of delta, because these two sort of naive Arctic circles or any smooth figures have parabolic shape, right? I can estimate this area of this region by multiplying delta by delta 1/2, so delta 3/2. Another question is what is the cost of in the action, and this can be also estimated by remembering that action, the energy is the energy of free fermions, so have this type of energy dependence on the density, rho to the power 3, and also looking at for example, this region and looking so that and noticing that the density deviates from its value 1 to the extent of delta to the power 1/2. So all this delta 1/2 times delta. This is the area times delta 3/2. This is rho to the power 3 gives you delta 3. So now we claim that this transition is in fact can be observed not only in this, the same transition will be observed with the same critical exponent, will be observed not only in non-interaction problem, but also in interaction problem. Imagine doing the same for XXZ chain. And just notice that near in this central region, the density of holes is very, very small. Therefore, they behave like free fermions. Okay, so this is a universal transition. And I probably don't have very much time now. There's a similar approach to the emptiness formation. Okay, so the Yasser was talking about how this picture actually influences calculation of Low-Schmidt echo. It's a mental picture. It's not, I mean, there is a calculations to be done. But again, if one just changes the size or radius of the circle to some imaginary, one gets similar Coulomb gas problem, much more complicated, however, still can be treated. And there is a transition as well. And it's quite similar. One can also define the corresponding quantities, even though their interpretation is somewhat tricky. But you have heard about this. Another transition of this type is transition. Remember when I was talking about producing emptiness by inserting the penalizing the trajectories. If I don't penalize the trajectories to go through this interval by infinite amount, but I penalize them a little bit, I can still have some trajectories going by the interval, and the corresponding quantity, depending on the parameter S, is known as a full counting statistics. And as a function of the penalizing parameter, one has another transition, a slightly different kind, and I will just show you the picture. There's a Coulomb gas correspondence as well, so one can find the solution. So this is what happens when on two sides of the emptiness, full counting statistics emptiness transition, for large value of the penalizing parameter alpha, one gets emptiness, as was shown before. For smaller values of alpha, one still have some particles going through the interval, but again, there is a kind of merger of linear shapes in the form of these two deltoids and have this typical behavior like power critical exponent 2/3 near the cusps of all these deltoid and asteroid-like regions. And yes, so these are the typical trajectories. So the only thing which I wanted to say in the remaining, how many? Okay, in remaining time is the following. Okay, so up to now it was the free fermionic problems. They are quite non-trivial and beautiful, but of course many things rely on the tuplet structure of the corresponding observables, and the fact that tuplet determinants can be calculated via Coulomb gas. However, there is a complementary picture, which is the hydrodynamical picture, which doesn't really, in principle, need this type of structures. The hydrodynamical equations can be written down not just for free fermionic equation of state, but from some other equations of state as well. So this is their power. Of course, whether one is able to solve them is a different story. However, the picture remains the same. And this is what we managed to do recently with some of my collaborator by looking at the interacting type of problems, namely the problem of polytropic gas, which has the equation of state written here. This is the pressure as a function of the density. It's characterized by polytropic index gamma. For some technical reasons, it's good to parameterize gamma by a parameter n. I mean, one motivation. Sorry. Okay. So one reason of this for this parameterization is actually, well, okay, for n equals 0, special value gamma equals to 3, one recovers 3 fermions. For integer values of n, the solution is sort of, it's not trivial, but can be found explicitly. And but n doesn't have to be an integer. And namely, the very interesting and important case of weakly interacting Bose gas, where I remind you that the pressure is proportional to square of the density, remained inaccessible. In particular, one would be very much interested in the sort of emptiness limit shape for weakly interacting bosons. Of course, the solution for the emptiness probability was deduced by, well, my collaborators and myself some time ago, and because it involves some analytic function like gamma function, could be just simply analytically continued, but we had no idea what the emptiness shape looks like. And finally, recently, me and Sasha and me found a way to deal with this problem. I just very quickly say that this problem analogously can be solved by using this kind of ballistic solution using the Riemann invariance. And again, all the question is on the trivial right-hand side. It's a known solution in the real space. It's written in the nice book of Kamchatnov. The task was to continue to imaginary time and write down an appropriate right-hand side for this equation, appropriate for a density. And we succeeded doing this by some manipulation with contours and analytical continuation to non-integer ends using Pohammer contours, so on and so forth. So the result is here. Now we are able to produce, again, from this equation and the known right-hand side, the emptiness shapes for any value of the polytropic index, well, in a certain range, of course, because the gas still has to be thermodynamically stable. And well, maybe it's not very interesting because they all look the same. However, there is a different scaling law near corners. For fermions, all the scalings are the same. There is certain symmetry between time and space. For other values of polytropic index, it's actually these two corners still have the same 2/3 or 3/2 scaling, while these corners is problem or interaction dependent. And here I would like to finish. If there are questions, thank you very much for your attention.
Hello, does it work? Yes. Thank you very much for the nice talk. I'm a bit confused about the interaction. Do you understand? Do you manage to include interactions or not? In which form?
In a form, for example, it's inverse power law interactions which give rise to this power law equation of state.
But in terms of the quantum model, the particles are still not interacting, or are they interacting?
The particles are interacting. There are specific models which lead to these equations of state.
You do an instant-on approximation, so you get essentially semi-classical trajectories of the interacting particles. Did I understand correctly?
Yes, one can infer the trajectories. But well, this kind of semi-classical trajectories in some sense is it's a visualization. I'm just going along the density profile, and every time I accumulate density, I mean, number of particles equals to 1, I draw a line.
Okay, thank you.
Yeah, very interesting. I just want to add one point. I mean, you know, when you look at the 6-vertex model, you see exactly the same kind of pictures. And there you have sort of a natural interaction because instead of the fermions, you have, you know, quantum spin chains as your transfer operator. I mean, that's more complicated, but, you know, you have the same picture.
Yeah, I haven't mentioned it. I mean, I probably mentioned it in the list of the people who have said it. It's, I mean, by no means the statistical physics models were only non-interacting ones. There was a lot of work done by people.
Yeah, I was wondering about the following. So you showed this nice picture of Arctic Circle type of phenomenon. And it's known that the fluctuations near the boundaries, I mean, in many cases, they are governed by KPZ, essentially. I was wondering whether they were, okay, of course, within this hydrodynamic approach, it's very hard to capture these fluctuations. This is one of your points, I suppose, but do you see any physical observables that would be sensitive to these fluctuations?
Well, as an example, I can give that if one modifies a bit this solution, say, if I go just like this, maybe I will use this picture, for example, and if I impose some extra conditions on these boundaries, for example, that, I mean, the standard one, which looks like an emptiness. So in addition to producing this picture, I will also say require that particles don't go beyond a certain point and calculate the corresponding action. I will reproduce the 3/2 exponent, for example. But question of fluctuation is interesting. It's not in this hydrodynamic framework. One has to do some additional calculations, but the result will depend on the hydrodynamic, on these profiles. Yeah, this is 3/2 scaling as well.
Yeah, so concerning fluctuation, so you say the Hydro framework would not be sufficient, so why not fluctuating hydrodynamics of some sort?
Sorry?
Why not using fluctuating hydrodynamics in some way? Why would that not be sufficient?
Okay, we'll be happy.
Some macroscopic fluctuation theory or something like that.
Up to now, we haven't figured out how to do that.
Have a microscopic model in mind for every value of gamma, or only some of these?
Well, not for every, but for some of them, yes. So as I said, this n equals 1/2, gamma equals to 2. It's weakly interacting bosons.
Is it known how to construct microscopic models for generic values of gamma? Or?
Well, there are the interactions which fall as a power laws between the particles. Type of dipole interactions, for example.
Again, so